This is the fourth lecture of week 10. Here are some facts regarding drunk driving laws and traffic deaths in the US. There are about 40,000 traffic fatalities annually in the US. About a third of them involve a drunk driver. About a quarter of the drivers on the road between 1 a.m. and 3 a.m. have been drinking. A drunk driver is 13 times more likely to cause a fatal crash than a non-drunk driver. So drunk driving can be considered as one of the public policy issues because drunk driving causes a lot of externalities. For instance, when there's a drunk driving and traffic accidents, there could be sober drivers who are killed from the accident, and society can often bear medical costs of the accidents. So there is a lot of justification for governmental intervention. So are there any effective ways to reduce drunk driving? There are some specific laws to prevent drunk driving, such as mandatory punishment for drunk driving, or minimum legal drinking age that prohibits people from drinking under a certain age, and also some type of economic intervention such as alcohol taxes. So in order to investigate whether the beer tax has any effect on traffic fatality rate, we have a panel data set. So this panel data set consists of 48 states which are observed for 7 years from 1982 to 1988. So it's a balanced panel data set. And some of the variables that we have in the data set includes traffic fatality rate, which is going to be our dependent variable, and tax on a case of beer, which is going to be our independent variable or variable of an interest. We also have other related variables that could potentially affect the traffic fatality rate. So for instance, minimum legal drinking age and minimum sentencing laws for first DUI violation are some of the laws that could potentially impact the fatality rate, as well as the vehicle miles per driver and state economic data, which also could potentially directly have an influence on traffic fatality rate. So how can the panel data set help? So we may have a potential omitted variable bias from variables that vary across states but are constant over time. So some of the examples of this is the culture of drinking and driving. So for instance, some states may be more lenient about drinking and driving than other states. And this culture probably don't change that much in the time period that we look at, which is 7 years. And there are other factors such as the quality of the roads may be better in some states than others, and this could have a direct impact on fatality rate. And the quality of the roads can vary across the state, but it may be constant within states. So quality of road can be better in, for instance, Texas than Wyoming, but this quality of the road in Texas is not likely to vary that much from year to year. Since some of these variables are such as culture of drinking and driving or quality of the roads may be hard to measure or observe, what we can do is that we can use the state fixed effect to control for these unobservable factors that are potentially omitted or can cause omitted variable bias. There's another type of omitted variable bias that can arise from variables that vary over time but are constant across states. So some of the examples include improvements in auto safety over time. So over time, the cars have become safer because of improvement in technology. So installing all these airbag systems could have made cars safer over time, which reduces traffic fatality rate overall. And there could have been a change in people's attitude toward drinking and driving over time as well. But some of these attitudes or improvements can be hard to measure or observe. So in this case, since this is changing over time but are constant across the state, we can include time-fixed effects to control for these unobservable factors. So here we have 7 different regression models. The first model doesn't really control for anything. It just regresses the traffic fatality rate on beer tax. And as we have seen before, it's actually showing a positive coefficient, which is counterintuitive because it's saying that when beer tax increases, the traffic fatality rate also increases, which seems to be counterintuitive to what we expect. When we include the state fixed effect, you can see that the coefficient actually changes a sign to negative. So this is more in line with what we would expect. So when the beer tax actually increases, the traffic fatality rate decreases. We can also see that when we include time fixed effect on top of the state fixed effect, then the coefficient changes very little. So it goes from negative 0.66 to negative 0.64. So it seems like time fixed effect doesn't have a big impact on the estimated coefficients. Looking at the adjusted R-square, you can see that the first model that doesn't include any control variables has a very low R-square or adjusted R-square. So it says that only 9% of variation in traffic fatality rate is explained by beer tax. Once you include the state fixed effect, the adjusted R-square actually increases quite a bit. So here it says that almost 89% of variation in traffic fatality rate can be explained by beer tax and the state fixed effect. And the adjusted R-square increases a little bit more when you include the time fixed effect. Model 4 is the most comprehensive model that includes the policy variables that could potentially impact the traffic fatality rate, as well as the economic condition of the states. In this model, we can see that the main coefficient of interest, which is a beer tax, actually becomes smaller and is no longer statistically significant even at 10%. We can also see that the laws related to minimum drinking age, the coefficients are, none of them are statistically significant, and the only statistically significant coefficients are the ones that are actually relevant for state economic conditions. Model 5 Model 5 through 6 and 7 are sort of robustness check. So Model 5 actually excludes the state economic conditions. And you can see that now the coefficient of interest actually becomes statistically significant and larger. So this indicates that if you exclude the economic condition of the state, then this should actually cause omitted variable bias because the state economic condition is statistically significant when it's included and the main coefficient actually changes quite a bit. So in the model, in the complete model, we should include the state economic condition. Model 6 controls for the minimum drinking age in a different functional form. So instead of including dummy variables for different minimum drinking age, this one, Model 6, includes a linear variable called drinking age in the model. And you can see that the coefficient is actually quite small and statistically insignificant. And the coefficient actually doesn't change much from Model 4 to Model 6, indicating that regardless of whether you include the drinking age in a dummy variable form or continuous variable form, it doesn't seem to impact the main variable of coefficient that much. Model 7 only includes 2 years of data instead of 7 years of data that we have, and actually shows that the coefficient is large and statistically significant when you only use 2 years of data. So what are some of the threats to internal validity? So first is omitted variable bias. So there could be public education campaign that went into effect when the beer tax actually increased. In that case, since public education campaign is correlated with the beer tax, and this can also directly impact the traffic fatality rate, this would cause omitted variable bias. In other words, it's not beer tax per se that affects the traffic fatality rate, but it could have been public education campaign that went into effect at the same time as beer tax increase that actually affected traffic fatality rate. The second threat is the wrong functional form. So we're estimating linear regression model, but it could be that the right functional form is some sort of a nonlinear function. The third threat to internal validity is errors in variable bias. So when we're using the beer tax data, there could have been some errors in data collection, and the beer tax that we collected could have had errors, which could threaten the internal validity. The fourth threat is the sample selection bias. So if the data was not collected through random sampling, so it was actually collected in certain areas with low beer taxes, then this could actually bias our estimate. The last threat to the internal validity is the simultaneous causality bias. So in the first model, when we don't include any control variables or fixed effect, we saw that the coefficient of interest was positive, which was counterintuitive. And this could be because of the reverse causality issue. So in a case where the states are increasing taxes because there is a high fatality rate, this could actually result in a positive coefficient, because it's not that the beer tax is causing low fatality rate, but it's the other direction, where because there is a high fatality rate, state officials or policymakers may decide to increase the beer tax to prevent such high fatality rate. So there are some advantages and some limitations to using fixed effects. So some of the advantages are the fact that you can control for unobservable variables if they vary across states but not over time, or they vary over time but not across states. So you can control for these unobservable factors by including fixed effects. Also, the estimation of fixed effect is relatively straightforward, so it's pretty easy to estimate. Some of the limitations of fixed effect is the fact that the time lag effect can be important, and we haven't modeled that in our application. And also, we have to cluster the standard error in case there is an autocorrelation. Here's a little digression. So the idea of using many binary indicators to eliminate omitted variable bias can be extended to non-panel data or cross-sectional data. The key is that the omitted variable needs to be constant for a group of observations, so that in effect it means that each group has its own intercept. So let's look at the previous example of class size effect. Let's suppose that funding and curricular issues are determined at the county level, and each county has several districts. And you're worried about the omitted variable bias that can result from not being able to observe these county level variables. In this case, what you can do is to include the county fixed effects. So this would be a binary indicator variables that is equal to 1 for each county and is 0 if it doesn't belong to that county. And it needs to omit one of the counties to avoid perfect multicollinearity. By including the county fixed effect, you can control for specific characteristics of the county that we cannot observe.